Welcome to GER Hub. In today's video, I shall be discussing set theory under a course title General Mathematics 2, having the code MTH102. This may not be the course title or course code in your school. However, please focus on the topic set theory. Irrespective of where you may be offering this course from, it remains the same in content. So we shall be discussing set theory, and my lesson objective will be background on set theory. In today's class, I'm going to be segmenting set theory as a whole into different lesson objectives. So in today's lesson, I shall be considering background on set theory. Now, there are so many items I would want to give under my background on set theory, as you can see. So I'm going to be discussing the following: what is a set, what is not a set, notations for sets and set elements, finite and infinite sets, to mention all the set description methods, and to describe some of the set description methods. So those are the lesson contents under this background on set theory. Now, if you haven't liked our video, please smash a like on the video, and if you haven't subscribed to our channel, please endeavor to click the subscription button, as it helps the channel. Okay, it increases our base, and it also helps when you like our video to ensure that the algorithm on YouTube makes so many other people see this video. Thank you very much. Now let's begin. So let's start this class with defining what a set is, and that will be the first lesson content in meeting this lesson objective background on the study. So please take note: a set is defined as a collection of well-defined objects. Okay, so a set is defined as a collection of well-defined objects. Now quickly, I'm going to highlight two keywords: well-defined, and the other keyword is collection. So please take note of that. The first thing I want you to know is the definition of a set. What we refer to as a set in mathematics simply talks about a collection of objects we say are well defined. Now, let's go over to the first keyword. So the question is, what is a collection? In mathematics, a collection to us is not far from what it means in secular life. So a collection remains or is a group of objects. Okay, a collection is a group of objects. So please take note of that. So any group of objects to us will make what is called a collection. Now remember, we have just said that a set is defined as a collection of well-defined objects. What that means, guys, is that not every collection makes a set. So I'm going to put that statement here: not every collection makes a set. Good. So the question now is, under what condition will a collection be called a set? So that's the second question we want to answer. And please, that will bring us to this keyword, well defined. So you would see, after defining or explaining that adjective there, well defined, why a set or a collection may be called a set or not. So let's look at the keyword well defined. So objects of a collection are said to be well defined if they have at least one property or feature common to them. So now please take note: Objects of a set are, let me correct this, are said to be well defined if they have at least one property or feature common to them. Meaning that if a collection does not have objects that have one common property or more to all of them in that collection, then that collection cannot be called a set. Okay, so for a collection to be a set, the objects must be well defined, and by well defined we mean that the objects in that collection must have elements or must have a feature or property or more that are common to all of them. So let's see an example of what that means. Let's see an example of what that means quickly. So I'm going to put that under example 1. Now let's consider a set. Please take note, as you will see subsequently, and as I shall be explaining subsequently, when you list out the elements of a set, you put them in a brace, a curly brace. So let's assume we have the set that contains orange, book, and tree, and a car. So let's look at this set that contains 4 objects. Object number 1 is an orange, object number 2 is a book, object number 3 is a tree, and object number 4 is a car. The question is this collection, for the fact that orange, book, tree, and car have been brought together, makes them a group of objects, and because they are a group of objects, we can mathematically call them a collection. However, the question remains, is this collection of orange, book, tree, and car a set? The answer is a big no. So I'm going to say this collection, so I'm going to write here the collection orange, book, tree, and car is not a set. Okay, so the reason why that collection is not a set is simply because there is no clear property or feature that connects orange to a book. So what is the relationship between an orange and a book? Orange is a fruit, a book is a school writing material. Tree and book, what connection do they have? Tree and car, what connection do they have? Car and orange, what connection do they have? So because we cannot see one clear property that binds all of them, it must bind all of them or must be common to all of them, then it means that that collection remains a mere collection. It is not a set. Now let's look at the next collection. So what if I decided to do this? I decided to form a group or a collection containing orange, mango, pineapple, and let's say an apple. Okay, so this is also a collection of objects because I have brought together items or objects like orange, mango, pineapple, and apple. So it's a collection, okay, because it is a group of objects. Now I'm going to quickly tell you that this collection, the collection orange, mango, pineapple, and apple is a set. Now the question is, why is that so? It is so because orange, mango, pineapple, and apple, we can clearly see that there is one property common to all of them, at least one. The very fact that they are all fruits makes for one property that connects all of them. So orange is connected to mango, mango is connected to pineapple, pineapple is connected to apple, apple is connected to orange, mango is connected to apple, apple is connected to pineapple, apple is connected to orange or mango. So there is one property at least. That is, by at least we mean one or more that binds all of them. For that reason, this particular collection is not just a mere collection, it is a set. So when we say or we ask the question, what is a set? It is a collection of well-defined objects. Since the second collection, orange, mango, pineapple, and apple, have at least one property common to all of them, we say that that particular collection has objects that are well-defined. As such, the collection can be called a set. Now, let us go over to the next lesson content. What is not a set? Now, people often make the mistake of twisting the real definition of a set, which is the one above, to defining a set in this manner. They often define a set to be a set is a they often define it as a set is a well-defined collection of objects. Please take note, this definition is absolutely wrong. This definition is wrong. Okay, now why is this definition wrong? This definition is wrong, please take note, guys, simply because this definition of a set puts the property of well-defined on the collection instead of putting it on the object. So what it means is that it is not the collection that should be well defined, it is the object in the collection that should be well defined. Let me give you an example. Now, especially in this part of the world, or in any part of the world, this can happen. Let's assume that we have a hall. Okay, so let's assume that we have a classroom. Okay, we have a classroom of 50 students in capacity. Okay, let's assume this, that we have a classroom of 50 students in capacity, and this classroom is meant to address or contain students alone, but 50 students are of course human beings and can actually be classified as, so 50 can be classified as the capacity of that classroom. Now, what happens if you say a set is defined as a well-defined collection of objects? In other words, talking about the property of well-defined for the collection rather than the object, then it means that classroom of 50 students, when it holds the same classroom, when the same classroom holds 50 people, different from the students it should usually contain, it means that classroom at that point in time is a different set. This is not the case. So we don't put the property of well-defined on the classroom, we put the property of well-defined on the students. Okay, so it is the students inside the class because they can be moved to another class, or the people inside the class because they can be moved to another venue, that we attach the property of well-defined to, not the classroom. The classroom can contain 50 students on a certain day, but can be used as a venue to contain 50 people on another day. So the property of well-defined, I say again, should not be put on the container, it should be put on the students or the content. Now, in Africa, what is very common is oftentimes when we buy a particular container of milk and we exhaust the content, being the milk inside the container, we often may start using that container to put pepper, to put granulated sugar and the rest. So we end up using a Bonvita container or a milk container which formerly or previously contained milk, to contain other items when we have exhausted the content. So would you say at that point in time we use the container that earlier contained milk, which now contains crayfish, or which now contains granulated sugar, would you now say that that particular container is no longer is still a milk container or still a Bonvita container even when it contains pepper? The answer is a big no. So please, simply put, a set should not be defined as a well-defined collection of objects. Rather, it should be defined as a collection of well-defined objects. Remember, a set is defined as a collection of well-defined objects, it should not be defined as a well-defined collection of objects. The definitions look alike, they sound confusing, but please take note of which one is correct. Now let's move over to the next thing I want to discuss. The next thing I want to discuss is notations for sets. Please take note, I'm not going to dwell on this, but please take note, in mathematics, sets, okay, sets are represented conventionally. By conventionally, we mean by agreement all over the world. So sets are represented conventionally with uppercase letters, okay, while elements or objects of a set, while objects of a set are represented with lowercase letters. So I'll put the adjective here, corresponding, and I'm going to explain why. Corresponding lowercase letters. Okay, so let's stop there and let me explain. So sets are represented conventionally with uppercase letters, while objects of a set are represented with corresponding lowercase letters. What it means is that to represent a set, I could call a set, I could say, let A be a set. Now, please take note, A represents any arbitrary set. So let me even put that adjective there. So let A be an arbitrary set. Okay? Let A be an arbitrary set. Now, if A is what you use to represent an arbitrary set, that is just any set, then the objects of the set A may be represented with small letter a or lowercase letter a. Okay, so we would use lowercase letter a to represent any arbitrary element in that set. And please take note, this happens for B also. So if I use B, let B be an arbitrary set. Let B be an arbitrary set. So if I use B to represent an arbitrary set, then what it means is that the objects of the set B may be represented with small letters b. Okay, so any element in that set can be generalized as small letter b. So please take note, this happens for any letter at all. So if you use capital letter X, then the elements should be arbitrarily represented with small letter x. If you use capital letter E, the elements should be represented arbitrarily with small letter e. Now please take note, there's an exception to this rule. Take note of one thing, that I have used the word here may, implying that it is not compulsory. So you can actually have a set or use in set theory capital letter A to represent your set or uppercase letter A to represent your set, but the elements are generalized with x, small letter x. Okay, so but in any case, take note, uppercase letters are used to represent sets, and corresponding or non-corresponding lowercase letters may be used to represent the elements of the set. Okay, so please take note of that. Now, like I said earlier on, another thing you need to take note of is that when listing the elements of a set, we often use or put all of them in a curly brace. Now let's go over, let's do something here. So let's assume I want to describe a set containing A, B, C, and D. Okay, so I'm going to call that set A equals, and I'm going to put the elements small a, or lowercase a, small b, small c, and small d. Okay, now it could also be that I have 1, 2. It could also be that I have 1, 2, 3, and 4 as elements of the set. Let's use this in particular to explain what I had explained previously. So if you are using this, if A is your set, then it means that if you are using corresponding lowercase letter a to represent the elements of the set, it means that small a could be 1, that is small a could be 1. Let me go back to using equations. So it means that when using small letter a to represent any of the elements, it means my small letter a could have been 1, it could have been 2, it could have been 3, it could have been 4. Okay, so if the elements of a set capital A are to be described, most often they are described using lowercase, corresponding lowercase a. So in this case, a can assume 1, 2, 3, or 4. Now please take note of that. Then the last thing I'm going to say under here is this. Okay, so let me quickly put this under example 3. Let's put this under example 3. Okay, so I'm going to put this under example 3, and I believe that explains that. Now the last thing I'm going to say before we move to the next sub content is this. Please take note of one thing. Sets, when you list the elements of a set or the objects of a set. Okay, let's even start with putting this. The objects of a set are the contents of the set. So what we call the objects of the set are the contents of the set. Now please take note also, the objects of a set may be called any of the following. So may be called any of the following. So we could call the objects of the set, most commonly elements. Okay, so the objects of a set can be called elements. They could be called members. Okay, so if you don't want to call them objects, you could call them elements. If you don't want to call them elements, you could call them members. If you don't want to call them members, you could call them components of the set. But please take note, out of these three words I've mentioned, the most common is elements and members. So members of a set, elements of a set are the same as objects of a set. Now let's move on to the next thing I want to say, the final thing I want to say under this subcontent. Now please take note, a set that contains A, B, 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 and C, you may ask, contains how many elements? In set, we don't repeat elements. So a set like this contains 3 elements to us, not 1, 2, 3, 4, 5, 6, 7. So this set is the same as the set this: A, B, C. Okay, so there is no repetition in sets. So please take note, whether you list A, an element of the set, 50 times, B, an element of the set 3 times, and C, an element of the set 2 times, the set still remains in content A, B, and C. No repetition. Now let's move on to the next thing. Remember, this is a discussion on the background to set theory. Okay, so we are still discussing background on set theory. Now let's move on to the next sub content, which is finite and infinite sets. So I'm going to start with saying finite sets are sets whose elements are exhaustible in counting. Exhaustible in counting. Okay? Infinite sets, on the other hand, Infinite sets are sets whose elements are not exhaustible in counting. Okay, so now what does that mean? So if a set is finite, it means that the elements of the set are countable and exhaustible. So you can actually finish counting the elements of the set. It means that that set has a beginning and it has a known end. If a set is infinite, it means we may be able to tell the beginning and the first 3 or more elements in that set, but we cannot exhaust the counting of the elements in that set. So what do we do? To start with, let's take an example of a finite set. So if I put up a set like this, let's put up 2 examples of a set that is finite. A set that contains 1, 2, 3, 4, and 5. Okay? A set that contains the first 5 positive integers is called a finite set. So I'm going to say the set, of course it is a set because it contains number. The set this is finite because the elements of the set are exhaustible in counting. Okay, good. So we can actually count and exhaust the counting of the elements. Another set, and I want you to take note of what I will be doing now. Another set like this, 1, 2, 3, and 1, 2, 3 ellipses, and let's put 1000 here. This is also a finite set. So I'm going to say is finite because the elements of the set are exhaustible in counting. Now please take note, just because a set is large does not mean it is infinite or infinite. So if a set is large does not mean that the set is infinite. It simply means that the set may be finite but the elements are large. So large sets do not necessarily make for infinite sets. Okay, because in this case, look at the first case. For us to represent a finite set, we simply list out all the elements in the set, and if the set contains elements that are too large, what we do is to write out the first 3 elements by convention, put these 3 dots we call ellipses, followed by a comma, and then the last element in that set. So in this case, the set contains 1000 positive integers, the first 1000 positive integers, and I have listed the first 3 followed by ellipses and then the last element, which is 1000. So this set is still finite although large. Now when we talk about infinite set, an example of infinite set could be this: the set this that contains 1, 2, 3 ellipses and the brace closed is infinite. Okay, it is infinite because the elements of the set are not exhaustible in counting. So if you take a look at this set, you will notice that although you can count the elements of this set, you cannot exhaust the counting. You cannot finish counting the element. So the set this is an infinite set because, oh, let me correct this statement, is infinite because the elements of the set are not exhaustible in counting. You can count the elements but you cannot finish the counting, so it makes it infinite. Okay, it makes it infinite. Now that being said, I believe that is good enough, And if you have any questions, please feel free to drop your comments in the comment section. Now let's go to the next lesson content, which is to mention the set description methods. So for you to describe set in set theory, we use 4 basic methods that are categorized into 2. So set description methods are categorized into 2 groups. Namely, so I could group them into group 1 and group 2. So group 1 are theoretical methods of describing sets, and group 2 are pictorial method of describing sets. Good. So there are 2 groups of methods for describing sets, but altogether 4 methods. So the first group contains the following. So the first group of method contains the following as methods. So it contains A. The first method of describing sets is the method called the method of listing, also known as roster method. Okay, that is the first method. The second method is the method of set properties. So, and the third method, which is method C, under the first group, the theoretical group of describing set, is the method we call set builder. Or if you don't want to call it set builder, you could call it set theoretic notation. So under the first category of methods for describing sets, we have the listing method, the set property method, the set builder method, also known as the set theoretic notation. Then the second group or category contains the method called the Venn diagram, and we shall be discussing that subsequently, but not necessarily in today's class. So now, that being said, please take note of those methods. So we've mentioned those methods, all the methods we know for describing sets. Number 1 is listing or roster method. Number 2 is set properties method. Number 3 is set builder or set theoretic notation method for describing sets. Those 3 methods put together fall under one category we call theoretical methods of describing sets. The second category contains one method called the Venn diagram, okay, and that shall be discussed subsequently in my class on sets. So let us now go into describing the last content, the last lesson content. So the last lesson content says to describe some of the set description methods. Okay, so I'm going to use example 5 to describe the first method, the method of listing. Okay, so let's start with the method of listing. So the method of listing describes sets by itemizing or counting each member or element of the set. So how do you use the method of listing? You use the method of listing for describing sets simply by itemizing or counting each element of the set. Okay, so if you want to do that, Okay, so if you want to do that, all you have to do for the method of listing, let's say we want to describe a household having 4 children. So I'm going to say Rookie may be the name of the first child, Charles may be the second name, or the name of the second child, and what do you call it? Let's say Abraham is the name of the third child, and Kingston is the name of the 4th child. So what have I done? I have just used the method of listing for describing the elements of that set, and the method of listing requires that you mention all the elements in the set item by item, that is one after the other, counting them one after the other. Now that brings me to the next thing I want to say quickly. If you are describing a set using the method of listing, take note, the main advantage of this method, the advantage of listing method is that it helps you know all the items or elements. Let's stick with the word elements. It helps you know all the elements contained in the set. So let's assume that on a certain day your teacher wants you or asks you to note the students that were in class. If you use the method of listing, you would find it very easy on a second occasion or on another day to recall who was there in class and who was not there in class. So that is one advantage of listing. Listing helps you to remember or recall what elements were contained in the set. However, the disadvantage of listing method is that it is inefficient. For describing large sets. So let's assume in the first instance it was very simple to count elements, 4 children in a particular household: Rookie, Charles, Abraham, and Kingston. What if you were asked to count a battalion of soldiers? In that case, it becomes very difficult to use the method of listing, not impossible. But you see that in counting a very large battalion of soldiers, it becomes very difficult to use the method of listing, because the method of listing requires that you count all the elements of the set item by item. So that brings me to the second method, and this method is called the method of set properties. The method of set properties. Now, please take note. The method of set property describes sets by using at least one property, one known property, bounding the elements of the set. Okay, the elements of the set. So how do we use this method again, guys? The method of set property looks at a set and uses one known property, a known property of all the elements of the set, to describe the set. Okay, and that is the advantage of this method. So I'm going to write here as an example, if I were to describe the set that contain Rookie. So let me put here the set give me a minute. Okay, good. So the set Rookie, Charles, Abraham, and then Kingston. This particular set may be described maybe described using set properties as the set of siblings for a house or a household. Okay, so you will notice that the same set above, the set containing Rookie, Charles, Abraham, Kingston, I have just defined that set as the set of siblings. So I'm going to put this here. Let's bring this here as my example. So recall that we had used we had put up the set Rookie, Charles, Abraham, and Kingston as a set containing siblings of a particular household using the method of listing, which required that we had to count each of them. But using the method of set property, you will notice that the same set containing Rookie, Charles, Abraham, Kingston, I can look at it and tell that they are all siblings and therefore call it the set of siblings. And that brings us to the advantage of listing. So what then is the advantage of listing as a technique? You will notice that the advantage of listing as a what brings us to what then can we say is the advantage of the method of set properties? The advantage of set properties, the advantage of set properties method is that it helps to handle large sets. Okay, so you can use it to describe large sets. However, the disadvantage of the method of set properties is that it denies one the opportunity of knowing what elements are actually contained in the set. So if I come to you without you knowing that I was actually describing the set containing Rookie, Charles, Abraham, and Kingston, and mention to you that I'm talking about the set of siblings. Now the question is, who are the siblings in that particular set? If I don't tell you, or if you had no previous knowledge of who they were, then you wouldn't know what siblings I'm actually referring to. So listing as a method helps you know the elements in the set, but it's always difficult to use for handling large sets. However, set properties is one method that will help you describe large sets, but it denies you the opportunity of knowing the elements that were contained in the set. And that brings me to the last theoretical method of describing a set, the method of set property. So the method of set builder or set notation, so the method of set builder or set theoretic notation describes sets using conventional symbols. Describe sets using a set of conventional symbols. So I'm going to be discussing those conventional symbols, and thereafter we shall be taking an example. We shall be taking examples. Okay, so I'm going to be taking several examples, but please take note, the method of set builder otherwise called set theoretic notation, describes set using a set of conventional symbols, and we shall be seeing the examples as follows. Okay, so I'm going to start with reminding you quickly of what we've said earlier, that the method of set builder or set theoretic notation describes sets using a set of conventional symbols, and I'm going to be showing you here that the conventional symbols needed are this and that. So let's see. So I happen to have put up those conventional symbols, so let me put them here. So what are the conventional symbols? They are the following. Now, looking at them, you would see that the first conventional symbol there is the alphabet A, but please take note, you would see that this symbol A or the letter A represents any arbitrary set. It means that any arbitrary set means that it could have been B, it could have been C, it could have been D, it could have been any letter at all. It could have been a symbol, any symbol chosen to represent the set. Now remember what I told you earlier on. Every set is represented conventionally, that is by agreement all over the world, with uppercase letters, okay, while contents of the set, being elements, objects, or members, or even components, are referred to are represented with lowercase letters. Okay, so the first symbol or letter you use in set theoretic notation could be any arbitrary set. Okay, the second is any arbitrary element. So if A is the one representing the set, if we choose letter A to represent the set, then lowercase letter A will be representing any arbitrary element, A, small a, of the set A. Okay, so that is what we have. Then the next symbol under set builder notation is the bar. Okay, the bar, alternatively represented with colon, can be used in set theoretic notation or set builder notation, and when it is used, please take note, it does not have the same meaning as in our conventional English language. Rather, the colon or bar are respectively used to represent such that. So when you see them, you read them in set builder notation as such that. Now, the reason why it is important for students to know these symbols and what they mean and how they are used in set theoretic notation is because if you don't know how to read set theoretic notation, you cannot interpret set theoretic notation. And if you don't know how to interpret set theoretic notation, you will find it very difficult to solve problems in set theory, because so many questions in set theory are represented in set theoretic notation. It is the most flexible way of representing or describing a set, so to say. So the next symbol used in set theoretic notation or set builder notation is the comma. Okay, yes, the comma. The comma in set builder notation or set theoretic notation should be read as and. Okay, I'm going to be showing you how to use that in example 7. Now, the next symbol is the curly brace. Okay, the curly brace is another symbol which is a set enclosure. It helps you to enclose all the elements contained in the set, all the elements you intend to describe in set builder notation or set theoretic notation. Then the next is this symbol used for representing membership. Okay, so the symbol is used for representing membership. It is called the membership symbol. So it is read as an element or member of. So whenever you see this symbol, read it as an element or member of. Okay, so when you see that particular symbol, this symbol above, crossed, when it is crossed, it will now represent the non-membership symbol. Okay, it will represent the non-membership symbol, in which case you will read it as not an element of. So these are basically some of the symbols used when we refer to conventional symbols used in set builder notation or set theoretic notation. These are basically some of the symbols. So let's now move over to using them. Okay, so as an example, to wrap up this particular class or module on set theory, let us consider, I'm going to write out some of them for you, and I would want you to read them. Okay, so let's start with the first set, I'll come over here. Let's go to insert. So coming over to insert and equations, let's write the following. So I'm going to write the set A. Okay, so I'm going to put that. This is the first set. I'm going to show you how to read with these three. Okay, so let's see. This is I'm going to copy this. I'll put that there. Okay, so let's take our membership symbol rather from here. So I'm taking it from here. Okay, so let's use this to read our set builder notation. You'll see how easy it is. Okay, so it's not that difficult. Okay, good. So I've gotten one. Let's go for another one. I would love to use two. I would love to use two of them. So let's put another one. So what is the essence of doing this exercise? It is to help you read set builder notations, help you read them so that you can actually interpret them. Okay, that is the essence of this exercise we are to look at. So I'm going to put here this. Okay, good. So we are set. We are good to go. Now let's start with the first one. The first thing is this. How would you read this particular set? This is a set builder notation. Remember, set builder notation involves the use of conventional symbols for representing sets. So this is a set builder notation. Like I said, if you don't know how to read set builder notations, you won't be able to interpret them. And if you cannot interpret them, you cannot solve any problem involving them in set theory. So let's see how we read the first set, read the second set, interpret the first set, interpret the second set, and let's see how that goes. So now remember, I said A represents any arbitrary set. So I'm going to start, for reading them, I'm going to write the arbitrary set A, and that is because of this. So you can find here in my set builder notation, you have A equals. So I'm going to start with saying this set A, the arbitrary set A, my equal to will be read as is. Okay, and the open brace there stands for the set of all. So I'm going to use it to so I'm going to read it as this: the arbitrary set A is the set of all. Now coming into the brace, you will find A there, and what did we say? Any arbitrary element A. So this A here will be read as any arbitrary element A. So the arbitrary set A is the set of all arbitrary elements. Arbitrary in this case means any element. That A could have been X, it could have been C, it could have been D, it could have been any other element. So the set A is the set of all arbitrary elements, small a. Okay, now remember the bar has been used here. Let me put the second one. In this second one, let's use the colon instead of the bar. So remember, the bar, like I told you earlier on, represents such that. So I'm going to come here. The set A is the set of all arbitrary elements A. Then in place of the bar, I'm going to put such that. Okay. Now, the elements, such that the element A is a natural number. So that symbol there, N, represents natural numbers. Okay, so you can look at the link in my description below to see my video on natural numbers. So N stands for natural numbers. We are taking it one after the other, and I'm showing you how to read set theoretic notation. So let's start again. The arbitrary set A is the set of all arbitrary elements A such that the element A, so I'm going to put these A's for simplicity's sake. I'm going to put these A's in in quotation marks, okay, such that the element A is a natural number. Now remember, your comma is read as and in set theory, so in place of that comma you can see there this comma here after the natural number symbol n. I'm going to use and, so I'm going to say and the element A lies between 5 and 10. So let's now read it all together. I'm done with explaining that, so let's read it all together. The arbitrary set A is the set of all arbitrary elements A such that the element A is a natural number, and my comma will now be read as and the element A lies between 5 and 10. So if you now want to write out that set, what will that set contain? What are the natural numbers lying between 5 and 10? The natural numbers, take note, natural numbers are positive whole numbers. So in this case, we have to look for all the positive numbers that lie between 5 and 10, with 5 and 10 excluded, because your inequality sign there shows that there is no possibility of 5 being included, there is no possibility of 10 being included. They are strict inequalities. So we are going to mention all the elements that are natural numbers found between 5 and 10. So let's list them. 6 is 1, 7, 8 and 9. So these are the elements that lie between 5 and 10 that are natural numbers. Now that being said, let us quickly use that same technique to read. Now this time around, I'm not going to do the breaking down process. I'm just going to write straight. So I'm going to say the arbitrary set, okay, the arbitrary set B is the set of all elements, small b. But take note, we are using x to represent our elements, in this case the elements of the set. Remember what I told you earlier on, you could use any other letter, not necessarily a corresponding letter to the set, okay, to represent your elements. So I'm using in this case x, so I'm going to put x, okay. So the arbitrary set B is the set of all elements x, or you could use all arbitrary elements x, okay, such that the element x is an integer, okay, and the element x lies between -3 or -5 rather, -5 and 3. So that is the way to go about reading this particular set, okay. So the set B, the arbitrary set B is the set of all arbitrary elements x such that the element x is an integer and the element x lies between 5 and 3. Now I'm going to give you this as a brief assignment, okay. So do this and let me know in the comment section what you read the set as and what your results were for the interpretation. So let me put this for you. I'm going to put this as the set D, and I'm going to change this to D. I'm going to change this to D. Please, I'm going to put the link in my description for all my videos on number theory. You need to know number theory in terms of the different types of numbers and their symbols, different types of number systems and their symbols. Please look at the links in my description below to learn different types of numbers, number systems and their symbols, okay. It will help you in set theory. So let's see. So I'm going to put here, I'm going to maintain Z, and I'm going to put here -4, okay. So you tell me what your results will be in terms of reading this particular set and in terms of interpreting it. So tell me that in the comment section. Subsequently, I will see you in my next module on set theory. Remember, the video does not end here. Set theory continues module by module, okay, until we are done. So thank you very much for watching this video. Please drop a like on the video and endeavor to subscribe to the channel if you haven't subscribed. My YouTube analytics is telling me that more than 50% of the people watching our videos, if that's 50% or more, are not subscribed to our channel, but they keep watching our videos. They don't like our videos. They don't drop a comment on our videos. Please, if you fall into that category of people who have not subscribed to the channel, please drop a like on the video and endeavor to subscribe to the channel, and I'll be seeing you in my next module on set theory. Thank you.